Welcome back. Again, my name is Brent Langston, and this is Creating Effective Container Images as voted on by the audience in the last session. So what we're going to take a look at is basically what it takes to build a Docker image, some best practices around it, some language-specific items that might be helpful, and then we're going to mention some tools, some tooling that you can use, and then hopefully at the end we'll have time to do a demo where we take a, let's just say, inefficiently written Docker image, Docker file, and build out of that, an effective Docker file. So what are layers? A Docker file builds an image, but it's not a flat image. It's actually an image of layers. And knowing how the layers work can help you sort of start to understand what is the right direction when I'm building my Docker file. So container layers are simply information that is written and then potentially overwritten in a future layer, to the point where we're at the very top, where when we launch our container, we have an ephemeral read-write layer for things that can go on in the container while it's running. So why does this matter? Why should you care? Because you should care because when you have more layers, then there's a chance that your image is overly large. The larger the image, the more it takes to download. As you do deploys, these downloads add up. They cost bandwidth, they cost transit time, they cost deploy time. So building an efficient Docker container is very useful and can pay off dividends. Smaller images can also mean smaller attack surface. So if you put less into the image, then there's less that is potentially outdated and less to potentially be used as an attack vector. Okay, so how can I reduce my layers? Well, one thing to just keep in mind is sharing is caring. Sharing is very useful. So, for example, try, if you can, and standardize on the same base image, or at least a handful of base images. At places that I've worked in the past, I encouraged polyglot development, but that didn't mean that we all just, it was the Wild West for images. I preferred that everyone start with Scratch for Golang or anything compiled, and if not, then try and use Alpine. So those were our two standards, and then there was a process if you needed some other image, a process for just, making that happen, but we tried to keep it limited. So if you can't do it in Scratch and you can't do it in Alpine, then let's look at, are we doing the right thing to begin with? And if we decide we're still doing the right thing and you need Ubuntu or something like that, then we'll do it. But for the most part, we try to limit the base image so that as we push things out, we have a shared starting point and we don't have to re-download the base image every time. Limit the data that's written to the container, and then chain run statements together. We're going to try and look at all of these things in a little bit more detail, and then prevent cache misses for as long as possible. So we're going to look at techniques for that. So basics of a minimal image. A Docker file is a series of instructions for building an image. So if you look at a Docker file, and we'll take a look at this in a minute, you'll recognize that it's just a bunch of lines. And as you read the lines, you can sort of begin to understand that the lines are simply commands. So think about for a second before you were using Docker. You needed to build a server. And the server, maybe you decide that server needs to have Ruby installed, Rails, a bunch of gems, and then your app code deployed to it, and so on and so forth. And so through your config management, or maybe before you adopted config management, you would log into the server and you would run commands that would set up everything that you needed, all of your prerequisites. That's what a Docker file is. It's effectively a recipe on building the end state of your image. So the thing to note, though, is each line that you executes in a new layer. And anything that you've done before that is permanent. So it is always going to be in that image. There's no undoing it. Let me give you an example of this. Let's say, for example, that you need to download some piece of software. So you curl a tarball to your server. You then explode the tarball. You then run make, and then you delete the tarball and delete the directory where it was exploded. So make install, etc. So that's a very common pattern, right? When you're installing stuff on a server. If you were to take those same steps and just put them into a Docker file, think about what would happen in each of the layers. First, I would curl the tarball, so that's going to take up space in a layer. Then I would explode it, so that's going to take up 10x the space in a new layer. Then I would run make and maybe then make install, so that's going to add more in new layers, either one or two. Then maybe I'd think, okay, well, now I'm going to delete the tarball and I'm going to delete the directory that I exploded everything into. Do I get that space back? No, that all happened in lower layers. So those layers are now locked in, they're read-only. That data is still there. It won't be presented to me. If I just look at the top layer of the container, that data will be erased, but it's all still there in the lower layers. So that makes for an inefficient container. So you can't simply take the commands that you use to build a server and run those exact same commands and build a Docker container. That's a good starting point, but hopefully now that you're sitting here, maybe you've done that and you can think, I need to go back and fix that. Cache is another critical thing about Docker. So as you build layers, think about, I love using Ruby because it's so slow, but Rails, I have a Docker container that I wrote with Rails, and for me to do a Docker build, every time I change my app code, it can sometimes take forever, and the thing that can make it take a long time is re-downloading, the Ubuntu like apt-get, updating packages and stuff like that. So I want to try and do that as little as possible. Every time I make a change in a Docker file, I change one line of the text of the Docker file, then Docker knows, it's very efficient at recognizing changes. And it knows, okay, everything above this line hasn't changed. I don't need to rebuild that layer. Everything starting with the change, I need to rebuild. And because I've invalidated that layer, every layer that follows needs to also be rebuilt. So think about as you're building a Python package or you're building Ruby or something like that, you tend to install pips for Python, gems for Ruby. If you put that as one of the top lines of your Docker file, and then you go change the list of libraries that you need installed, you're going to invalidate every single layer after that. And so you're going to be constantly having to rebuild all of the layers of your Docker file. If you put your app code, step 1, start with Ubuntu. Step 2, copy my app code. Well, obviously, every time you are changing your app code, you're going to rebuild your Docker file. If that's layer 2, then you're going to have to rebuild every single layer every single time. That's going to be inefficient. So using cache or knowing how Docker caching works will help you build a more efficient Docker file. So this is a very basic Docker file. It looks fine. We start with Ubuntu latest. We then run apt-get update, and we do apt-get install Python stuff. Then we copy our application. We change directories to our application. We run pip install requirements. We expose 5000. We set up the entry point to be the Python command with application.py as the argument. This looks totally normal, right? This is perhaps even a good Docker file, but it can be better. So one way to make this more efficient, we started with Ubuntu latest. Ubuntu latest on its own is 458 megs. Think about that for a second. I haven't added anything to it, and I'm starting at 458 megs. So I know that you might like Ubuntu. That might be what you run on your desktop. But that doesn't mean that it's good for Docker images. Get used to smaller distributions for Docker images. It'll pay off for you in the long run. One of the smallest, and now the official Docker image, is Alpine. So Alpine, the base image for it, this, by the way, is the Python version of Alpine. It's at 86 megs. The standard Alpine base image is 4 megs. So you can go from something very big to something very small by making a really simple change at the very beginning, switching from the stock Ubuntu image to the Python Alpine image. So these are some base images that you can take a look at. Debian, 123 megs. If you like Ubuntu and you want to stick with Ubuntu, I mean, come on, Ubuntu Debian, are you really going to notice the difference in a container? Switch to Debian and you'll save 300 megs. So that's an easy choice to make. Fedora, if you like the Red Hat ecosystem, you can get some, well, relatively small image sizes out of Fedora. So definitely, explore that. But I would really encourage you to bite the bullet and look at Alpine, get used to its packaging system, get used to its package names, and just sort of add that to your repertoire of stuff that you know about, because 4 megs. I mean, that's really hard to beat. Okay, when do you want a full base OS? I've had to do this once or twice, and for this I've done Ubuntu, I've done CentOS, I've done Fedora. But the reason that I needed it was to actually test running security scans that test an operating system. So it was like the container needed an operating system in order to run all of the tests that it needs to run. It needs to validate that Etsy password exists and Etsy shadow exists and expiration is set. And all these normal operating system level tests, I just stuck them all in a container, but ran an operating system in the container. Very rare. It's probably something that you don't normally need to do. So back to our original image. Remember Ubuntu latest? The next thing we did is we ran apt-get update. If we make this simple change, we're copying, we're starting with Python 2.7 Alpine. We're then copying our app. We're setting up our directory for our app, and then we're running pip install. We go down to like 90 megs or something like that. Super, super good change. Even better change, though, is to take that and copy requirements first. Think about, okay, when would requirements get copied in this file? When we copy the app code. But that's line 2. Every time I'm building a container, it's probably because I changed the app code, which means every time I'm building a container, line 2 is new, which means every layer starting with line 2 is invalid. If I am not changing requirements.txt quite as often, then let's copy it over first. Let's do the pip installs after that, and then we'll copy over the rest of the app code. By doing it this way, I don't have to sit through pip installs on every container build. I only have to sit through those when requirements.txt changes. So I change a version of pips, I invalidate layer 2 and I build everything after that. But if I never change that stuff, once I've sat through that build once, I get to reuse that layer over and over and over again. So cache, it's your friend. Take advantage of it. It changes the order that you might choose to do things, But once you have this pattern figured out, it's easy to spot and it's easy to reuse. So, recapping. Layers represent file system differences. They add up. As you make changes in future layers, former layers are locked in and they will never be changed again unless you change the way they get built. You can build and run everything the same regardless of the container operating system though. So just use Docker build and Docker run. So we take all of these different behaviors and we sort of wrap them in something that is the same everywhere, every time. So it's this, I'm building the container the exact same way on my laptop as I am on my server, as I am, I don't know where else you might do it, but everywhere. It's always the same. So that's what's really cool. Okay, so Docker files. We're going to start out again looking at our Docker file. So this is the big one. I may have repeated this slide, actually. Yes, I did. Okay. So thing number 2 to note about Docker files, again, layers are line by line in the Docker file. So that means if you can continue a line, then you can save space. So remember my scenario where I'm downloading a tarball, I'm exploding the tarball, I'm running make install, deleting the tarball, deleting the source code. What if I did all of that in one line? Now all of a sudden I'm not paying for that space. I'm not spending space to hold that tarball, spending space to hold the exploded tarball. I should use line continuations and do that entire operation with conditional executions on one line. And that's what we see here. We have one line on the screen. Obviously, it's broken up, but it still counts as one line in the Docker file. It's a run line where we run apt-get update, apt-get install. We list out all the packages that we're going to install. And then, and conditional execution, we run rm-rf, the apt cache. So we get rid of all of that cruft that got downloaded just by us using the package manager. Think about it for a second. In a container, we're never going to use that package manager again. Once it's built, it's built. So we don't need all that stuff, and therefore we should get rid of it so that it doesn't take up room in our container. So this is a very common pattern for efficient containers. So switching users adds layers. Basically, again, every line adds a layer. Now, it's a metadata layer. It doesn't necessarily add space, but it is a layer nonetheless, and therefore it locks in everything that has happened up to that point. Avoid adding large files. So you see here kind of the example I've been using, where we're downloading or we're adding a tarball, we're extracting it, and then we're running make. Put it all in one line with conditional execution, and that way you aren't giving up all the space of storing the tarball and the exploded tarball. Although I'm missing the delete at the end of all that. Bad example. Pretend that was there. That should have been there. So, oh, here we go. Even better example, including the delete. So I am downloading, I'm untarring, I'm making, and then I'm RMing the tarball. Now, language-specific stuff. So I alluded to this earlier. There are certain languages that can take advantage of certain conditions in Dockerfile. One, for example, is Golang. So with Golang, you know that when you build, what you end up with is a statically linked artifact. That is awesome. You can build statically linked artifacts with C. You can build statically linked artifacts with Crystal. You can, for example, with Java, build a Java jar that has all of your dependencies put together. So these are all languages that you can take advantage of this style, but basically build, and then once you have your artifact built, copy it to a Scratch container. What is a Scratch container? That from line means start with nothing, start empty. So from scratch, you're starting with 0 bytes and empty nothing. And then you're copying in your artifact, and then you're setting the entry point as your artifact. So this is the smallest container you can possibly build. It's as big as your artifact. And it's easy to distribute, it's easy to run, because you can run Docker anywhere. So anywhere Docker can run, you can run this, and this makes it super easy. So again, what is Scratch? It's a special empty Docker file. You can use it to build your own base images. If you ever look even at like complicated Docker files like Ruby, if you look at the official Ruby Docker file or the official Python Docker file, you'll see that it starts from scratch. And it actually explodes a tarball into the container and builds a whole Linux file system from that tarball. So Scratch is where eventually everything traces back to. But if you start from there, then you know you're going to have a Docker container that's as efficient as possible. Okay, Ruby. Official images for Ruby are huge. I don't know why. But if you just change out the base image from the official one, then it can pay off huge dividends. So you can see in this Docker file, we're starting with Alpine 3.2. Instead of starting with the official Ruby image, start with Alpine. You know your starting point is 4 megs. Then you can, APK is their package manager, APK add the stuff that you need, and then delete the cache. This should have been a line continuation, by the way. So notice that deleting of the cache really isn't going to help you any, is it? Node.js, also very small, very efficient. Again, just like with Python earlier, where we copy over requirements.txt, with Node.js, that equivalent is package.json. So copy over package.json, install your npms from it, then copy over the rest of your code. That way you're not invalidating layers. Java, this is more than just for Java, but it's really handy for Java because when you're doing Java you run tests, the tests often take a lot of additional software to be able to run. But you don't need that software to live in your final container. So Docker introduced, I don't know, maybe a year ago, something called multi-stage builds. And what it is I'm going to start with a container, start with a big container if I want, and I'm going to run some commands. And then when I get to the point where I've built an artifact, I can then create a second container and copy something out of the first container into the second, and then throw away the first container. So that's a multi-stage build. I can build an entire jar, I can do all my Maven testing, and have everything that I need for the testing, then turn around and take that jar and copy it into an empty container, and then run that and distribute that container around. And I have a small Java container, even though I had a big Java build environment. So here's an example of doing a multi-stage build. In multi-stage builds, you see that I'm starting with from Ubuntu, 458 megs, or whatever it was, as build-env, and I'm doing all, installing apt-get, installing make, and then adding my source, running my build. Then my second container is from BusyBox, which is still really tiny, and I'm copying from build-env the built application and then exposing port 80. So you see that in this multi-stage scenario, I'm going to distribute a really small container even though I started with a container that was hundreds of megs. Multi-stage builds, really handy. Yes, sir? I mean, it takes seconds longer because, well, longer than the Ubuntu, seconds, because That's what's really taking a while, that running your tests and all of that. To add on the second container, BusyBox, and then copy the file is just, I don't know that you would notice the difference. It's 5 seconds more, maybe. So the savings in space will be where you get back all of those extra seconds. So you won't be downloading 500 megs on every deploy times every server. You'll be downloading 5 megs, times however many servers. Tools are here to help. So basically, what are tools for? This is my coworker, Abby. You see I liked. Basically, how can you, but mostly me, do less work? So tools are the answer to that. Tools will help you do less work. Think about my example from the earlier talk, keeping track of vulnerabilities. Like if you had to do that by hand or by manually track every single library that you use across hundreds of microservices, that could just drive you crazy. That's more than a full-time job. So there are tools that can help you do that. This is an example of using a Docker security scanner. So the workflow goes basically like this. I build a Docker container, I push my Docker container to some registry, and then that triggers a scan. So some scanning service, earlier I mentioned Twistlock, some scanning service comes along and notices that you pushed a new version of your container. So it goes and grabs it, and then it introspects every layer, not just the top layer, and looks at what's in the container, and then it alerts you if there are any known vulnerabilities, and it does that on an ongoing basis. So as long as that is the one that you have deployed, that version of that container is what you have deployed, then I care if a vulnerability is discovered. So services will keep track of all of that and then will alert you. There was a service that was built into Docker Hub that would do this for you, but I think I just logged in a week or two ago and noticed that they've sunsetted this. So it may still work for some people, but I don't know that it will work on new repositories. Okay, so let's try and actually do this live. This is kind of funny because I was like, well, okay, where am I going to find an inefficiently written Docker container? And then I thought, well, okay, where will I find any Docker containers? So I went out, the very first place I looked was the AWS samples GitHub repository, where we actually have an ECS workshop. I've run this workshop, I don't know how many times. I've seen it run countless times more. I never bothered looking at the Docker file until I was writing this talk. And this Docker file is, well, not awesome. So it looks awesome, though. So, okay, let's drop out of this and go to the command line. And by the way, I forked this repo so that I can make changes. But if you want to sort of do this on your own and examine it, you can either look at my fork of the repo, and I've saved all of the iterations of the Docker file for you to look at, or you can, figure it out on your own from theirs. Okay, so the original Docker file looks like this. So by the way, I only looked at the Iridium client. This is a workshop where we launch a series of microservices, and one of these microservices we've named Iridium. So this is just the client for Iridium. The original Docker file looks like this. It's actually pretty to look at. It's easy to read. We start with Ubuntu 14.04. Well, okay, now that you've sat through enough of this, well, that's mistake number one, right? Just don't start with Ubuntu. Then we do an apt-get update. Then we do an apt-get install. Then we set our work directory. We download getpip.py, and we run getpip.py. Now, I don't know why we're downloading the pip installer when, there is a pip installer for Ubuntu, right? But we do. We set our work directory again to a different directory. We build a virtual env. Why do you need a virtual env in a container? You don't. This is I can tell after I get to this point that whoever wrote this is just copying instructions straight off of how to build a server, right? They're not making a mistake. This is just not Docker style. So this is inefficient. They're doing pip installs, and then they're copying requirements.txt, and then doing a pip install of that list. Then they copy over the app and execute the app. So we can do better, right? All right, so let's take a look. An easy win would be to swap to Debian Stretch Slim. So let's take a look. If I just build this as is, the way it's written, the image is 568 megs. So we know that most of that is Ubuntu. Let me show you a trick, by the way. Docker history on the image ID. And we can see every layer, and we can see how much space is in that layer. So if it's missing, that's probably because it's in the from. So line 1 from Ubuntu. These are all the lines that were used to build the Ubuntu image. And then starting with the layers that have IDs, those are my lines. So notice that line 3 adds 232 megs. It's where I'm running apt-get install. And then another 10 megs, another 12 megs, 25 megs, 43, and so on and so forth. So we can basically look at this and we can know where can I optimize. Once I've squeezed the space down to hopefully one layer and gotten that layer to be as small as possible, then I'm as optimized as possible. I'll still probably have some bytes here and there, but for the most part, if I have one layer that does what I need it to do, and all of the space is in that layer for the most part, then I know I'm optimized. So, Docker images, grep client. If we just change one thing, change it to Debian Stretch Slim, we know that going from Ubuntu to Debian can save us hundreds of megs. So let's grep for Slim. So client Slim starts off using uses Debian Stretch Slim instead, and I'm down to 388 megs. Awesome. That's much better. But still, I could probably do better. If I Docker history this, then I can still see that I have, 55, 200, 16, 14, 16. I still have some, space. There's another 43. So I still haven't figured out how to put all of those in one layer. Okay. What more can we do? Well, we can switch to Python 2 Alpine. Remember Alpine, much smaller. This is the one that Python builds for you and provides it. So it has Python, in my case, Python 2.7, because I'm saying Python 2 Alpine. So let's switch to that. Let's see. So Python 2 Alpine, when I build, gets down to 73.2 megs. Let's take a look at the Docker file. Alpine. So I've switched from Python 2 Alpine. I switched the package stuff. Instead of apt-get in Alpine, it's APK. A few of the package names change also. But for the most part, I kept all the packages in there that had been in there before, even though they probably weren't necessary. Like I never saw anywhere that used get, so I don't know why the get package is in there. But I left it in just for fairness' sake. We still are downloading the getpip.py and all that stuff. So I haven't optimized any of that yet. Let's take a look then if we do some more optimization. We'll get rid of some of the superfluous layers and the pip cache. When I make this change, I go from 300 megabytes to 275 megabytes. And that Docker file looks like this. So I still have my apt-get upgrade and adds. I got rid of the downloading getpip.py and all that, and I just used the package manager's pip. And that's about it. So if I then try and combine, remember combining run statements is handy. So if I combine all the run statements that I can combine, I get down to 162 megs. Even better. Let's take a look at that one. So I'm copying in requirements. I'm doing the APK upgrade and installation in one line, and then I'm copying over my app code. So I've gotten down to only, 3 lines of actual work. Pretty handy. Can we keep going from here? Let's see. Let's take a look at the history of the image. Okay, so starting at the bottom, I'm starting at 4.82 megs. Again, this is all stuff out of my control. It's in the from Python 2 Alpine. Looks like they add in 61.2 megs, then another 6.56 megs. Then my big layer is 88.7 megs. But that's really it. So everything all of my commands have been squeezed into one layer, and it's roughly 88 megs in size. But the rest of the space is coming from my base image that I didn't build myself. But you know what? I did choose it. So what if I made a different choice? What if instead of Python 2 Alpine, what if I just use Alpine? So let's not use the Alpine that the Python community builds and distributes. Let's use just straight up Alpine, and let's add in the Python bits that we need. So when we do that, my image goes down to 72 megs. So I started at 568 megs, and in 10 minutes, I'm down to 72 megs. Think about what that does for deploy times. At Tumblr, we used to have 1,000 web servers just for our front end, and we would do deploys, I don't know how many times a day, dozens of times a day, but let's say, for example, that we had 1,000 and we did 10 deploys a day. And if we were at 568 megs, round down to 500, we would be spending 5 terabytes of bandwidth a day on just deploying code. That would be 5 terabytes a day that we couldn't use to serve traffic to our customers. So that would be terrible. If we can reduce that down to 72 megs, then we have won by almost an order of magnitude. We have reduced the amount of bandwidth necessary to do deploys quite noticeably. So what does this file look like? So I'm copying in requirements. I'm running my APK upgrade and package commands. And then at the end of it, I am RMing the package cache and finding all of the precompiled PYC files. I don't need those because they just get rebuilt when I start my container. So let's just get rid of them so that I'll save the space. And then I copy in my product, my product.py, and I execute it. So this container behaves exactly the same and is almost 90% smaller than the original container. Another side effect of having large containers, especially when you're using orchestration, the hosts that you're downloading containers to will eventually fill up. So every time you download 568 megs of image, that has to be stored somewhere. So over time, Docker doesn't clean those images out. Now, it will unlink images. In those unlinked images, you can issue a command, docker image prune, and it will prune any images that are unlinked that'll never be used again. So that's great, but you have to think to do this. Or if you know I'm no longer running any of these images, you can do docker system prune, and this will clean out any images that are no longer linked to any containers. So no running containers, get rid of the image underneath. If you ever need it again, you can re-pull it. So this is handy to build in. All of the good orchestrators build this into their client already. Kubernetes does this for you. ECS does this for you. I don't remember what schedule it does it on, either one of them, because it's pretty good at it. But it's good to be aware that this is something that you need to do. If you're ever lacking space on your laptop and you use your laptop to build images a lot, go back and look. It's like I cleaned up like 20 gigs of old images off of my laptop. Unfortunately, then I thought, oh man, that would be a good demo for this, but there's no way to get them back. So garbage collection is what that's called. Clean up after your containers. Now, if you're using something like Fargate, you never have to think about it, right? Because you don't manage the instance. So the instance will never fill up on disk. As you rotate out your containers, they're probably going to be coming up on new instances that are clean. And then we, cycle those disks and clean up everything under the covers. So, looking forward to the future, there's always going to be more. So there's always newer things coming out. Pay attention to social media, pay attention to white papers and blog posts, but try and keep up with things that are changing, because there will always be a newer way to do something that you can do today. So what have we learned? Less layers is better, is more. Share layers whenever possible. Choose to build your base image wisely. That could just be making a choice of what to start with, or it could be starting from scratch. So depending on your code or your interest level in building your own image, you could potentially start from scratch. Not all languages have to be built the same way. The way you build Java might be vastly different than the way you build Python. Python might not benefit greatly from multi-stage builds. Node.js might benefit slightly more, and then Go and Java might benefit greatly from it. Keep it simple. Try and avoid the extras. Don't install Vim Enhanced, right? Because you're never going to log into that container. You're never going to run an editor. So if you do, you're probably doing something wrong. So just, don't install the things that you normally install to your server, because this isn't a server. This is just to execute your app and nothing else. And then use tools. They're here to help you. They're here to make your life easier. These are some useful links. I know you can't read this very well now, but definitely check it out when you get a copy of the slides after filling out the survey. Thank you guys very much. And are there any questions I can answer? All right, cool. It's like beer 12, I can't say it right. It's not beer 30 yet. So I hope you guys have a good day, and come find me if you have any questions later on. Cool.